All right, so we're moving on to talk about electric potential. Electric potential is going to bring back some ideas of your mechanics course, where we're talking about potential energy and kinetic energy and how energy is transferred back and forth between the two. And you're going to see some of that, and we are going to tie some of this together in some of our work problems where you're going to find the electric potential energy and it's going to make a charge move, and so you can find the speed of the moving charge through ideas of conservation of energy. So we're going to start off talking a little bit about how electric potential energy is similar to the mechanical potential energy. And if you think about a ball rolling down a hill where it's due to gravity, it's just going to roll right down the hill and you have to do work to get it back up to the top of the hill, charges and fields are very similar. If the charge is going to head to a positive charge is going to head towards the negative charged plate, it's like rolling down a hill. It wants to do that in the field. But if you want that positive charge to get closer to a positive charged plate, somebody or something is going to have to do work to get it there. And that something is generally some kind of a force. And so the electric field is going to apply a force and it's going to try to either attract or repel. And you can apply a force or something else can apply a force to move the charge in the opposite direction. And depending on who's doing the work, either the field or an applied force, you're going to talk about negative work and positive work. And so if you're going to consider this point charge, you want to move a positive charge towards another positive charge. So we've got little q stuck down, and big Q, we're going to push it towards little q. And so the electric force is pushing it away, and our force is pushing it towards, and we manage to get from P1 to P2. What we've done is we have done work on the charge, and because we've done that, we have added potential energy into there. And the other way around, if as the charge moves away, it's going to lose potential energy and it's going to gain kinetic energy once we let go. So electric potential energy, the symbol is U, and it's in joules. You'll also see volts per coulomb in here. It is a scalar, which is going to make the math in here a lot easier because we don't have to worry so much about directions. And superposition will apply. So just like when we were dealing with charges, forces and charges, you could add all the forces up, but you had to deal with it vector-wise. This one, you can just add them all up, but you do have to watch positive and negative. So the positive and negative of the charge is all you really have to pay attention to. A little bit simpler. And so the equation does not look simpler, but basically all that it's telling you is that you're summing up the potential energies of each of the charges, and you do need to keep the positive or negative value of the charge. And so here's a little problem. You kind of do it in multiple steps. We're going to find out how much work is done when you're placing three charges into a triangle. So we start off with Q1, and it's placed. There aren't any charges present, so there's no work done. It's just, you just put it there, didn't require anything. Then you're going to add in Q2. And so we're going to have to find the work to get Q2 near Q1. And so you use the equation KQ1, Q2 over the distance between the two charges and ended up with negative 1.2 joules. And then we have to add in Q3. So now it's how much work did it take to get Q3 near both Q1 and Q2. Same equation. You're going to take the distances between the two different charges. You're going to add that up. And now we have the work from putting Q1 down, which was 0, the work from adding Q2 in, and then the work from adding Q3 in. And then you add them all up, and that tells you how much work was done. And so here's kind of a summation of what happened physics-wise. You place the first charge, no work done. You bring in a positive charge, and you've done positive work because the potential energy is increasing. You can think of it a lot like, moving up a hill or squashing a spring. You're just adding some energy to the system. And then if you bring in a negative charge, negative work is done because it's going to move away and potential energy decreases. Rolling down a hill. what we're doing. So now we want to talk about something a little bit different, and this is going to lead us into circuits and other things. It's just a more usable unit for concrete things, and that would be electric potential. And so that's the energy per unit charge. And when we're talking about voltage, we're not talking about energy. We're talking about how much energy is in a unit charge. And so that's what it comes down to. It's kq over r for a point charge, and that'll work in most of the instances that we have. You can treat them as if they were point charges. And when we're talking about potential difference, you're talking about the difference in voltage or electric potential between 2 points, point A and point B. So you measure it here, and you measure it somewhere else, and you find the difference between the two, and it really is a change in potential energy per unit charge again. And it is joules per coulomb or volts. And so it's fairly simple. The math wise, here's a little example what voltage is needed to create 8/10 of a microcoulomb. It's a strange number. That much charge on a 10 centimeter radius Van de Graaff generator. Use the equation, plug things in. You get a pretty large number. Van de Graaff generators are fairly large voltages. Those are the ball things that make your hair stand on end and put out sparks that are so much fun to play with. And so, looking at the superposition idea, I took a problem with a dipole, and a dipole is when you have two charges that are equal but opposite. So in this case, they're both 2 microcoulombs. One's positive and one's negative. They're a fixed distance apart. This one's 4 centimeters apart. That's pretty far apart for charges. And then finding the potential at some point P. Notice, didn't have to deal with vectors. It's just straight line distances for this. And you just add them up. What's the voltage from P to 1? What's the voltage from P to 2? And add them together. If you're having trouble imagining a dipole, water is a dipole, for those of you that are chemistry based. A real life example for you. So voltage and electric fields basically come out of interaction of electric charges. And remember that voltage is a scalar, the electric field is a vector. Potential is a scalar. So you may find it easier to work with different things. There's kind of a tie between them, that obviously voltage and electric field are connected. So the mathematical tie is in a constant electric field, and where we're going to see this a lot is between parallel plates. You got the parallel plate capacitors, something where the field is constant. The voltage in that area is going to be the electric field times the distance between the two plates, or the distance between the two charges. So you have two charges. What's the voltage between them? Well, find the electric field between them, find the distance, and you can get the voltage, or the other way around. Of course, this is one of my favorite equations because it's volts equals ed, nice and easy to memorize, and for some reason that's stuck. So here's a pretty standard example. You've got parallel plates. They're some distance apart, and then pretty much, parallel plates, you can build up charge and build up charge, and then eventually they arc. And depending on what you put in between, you can delay or pile up more charge, and build it up and build it up. In this case, I picked air, and so it's just volts times the electric field that it would take to break down 3 times. Well, I guess the real question is how much voltage would it take to break down that electric field and cause a spark. So here's the electric field. It's 3 times 10 to the 6 volts per meter. And then the distance is 5 centimeters. And just if you do the math, you end up with 1.5 times 10 to the 5th volts, which once again, we're dealing with some pretty big volts. And it's lightning. So, it's going to be big. Anyways, so a couple extra energy bits here. I mentioned conservation of energy at the beginning of this, and so you're going to have to think back to those perfect ideas where you're at the top of the hill and it's all potential, and the bottom of the hill where it all turns kinetic, and how the energy transfers in between. We're going to be talking about, you've got a charge moving in a field that has this much potential energy. How fast is it moving? So you're going to set up that same idea where energy is conserved. The total energy is potential plus kinetic at all times. Here we know we have this much potential before it gets moving, and now we have this much kinetic. How fast is it going? Um, and then you'll see this is a unit you'll see a lot. It's called an electron volt or an EV, and where this shows up a lot is when they're talking about the great big accelerators, million electron volts, MEVs. So we're talking about lots and lots of volts when you start counting in electron volts, and a lot of that has to do with X-rays and some of the other things that are very high energy, and it's basically the amount of energy it takes to accelerate an electron through 1 volt. So it's 1 electron volt, and it's related to the joule. You can see that, so you can kind of see where those all come together right there. So that's kind of the first part of this lesson in a nutshell. Uh, Good luck on the check, and I'll see you soon. Bye bye.